Hi guys, welcome back to Nunley Math. I'm Aaron Nunley. Thank you for joining us for our lesson on congruent figures. Now this lesson is a part of our larger unit on the basics of geometry, where we're going to introduce some basic geometric terms, some basic geometric ideas that can be used when we're dealing with more complex geometric problems down the road. Now there are a lot of definitions in this particular unit, so we're going to spend a lot of time talking about what certain terms mean, as well as what those terms can indicate for us as we're looking at geometric shapes. So let's go ahead and dive right in. Congruent figures are two figures if they are the same shape and the same size. The same shape and the same size. Or another way to say that is all their corresponding sides and angles must have the same measures. Now, if you were with us for our unit on ratios and proportions, you will know that we already talked about similar figures, and we said that similar figures are the same shape, but they can be different sizes. When we're talking about things that are congruent, their shape and their size must be identical. When we talked about similar figures, we said that the corresponding sides had to be proportional and the corresponding angles had to be congruent. In the case of congruent figures, both the corresponding sides and the corresponding angles must have the same measures. We do have a symbol for congruent. It is an equal sign with a little squiggly above it. This is our congruent symbol. You'll remember just the squiggly sign by itself was the symbol that we used for similar. So, suppose I were to tell you that triangle ABC, that's this triangle right here, is congruent to triangle DEF. That is this shape right here. When I make this statement, there are lots of things that this tells me about the relationship between these two triangles. They are exactly the same size, they are exactly the same shape. But what that means is very, very specific. Notice that angle A is written first in this name, and angle D is written first in the name of the second triangle. And you'll notice that angle A has one mark in it, and angle D has one mark in it. All of these things indicate that if these triangles are congruent, that angle A and angle D are corresponding, or they are matched to one another, and as a result, their measures are congruent. In fact, I can go through each piece of these triangle names and I can do the exact same thing. So let's look at the angles first. I already told you that angle A has the same measure as angle D. I can tell that because they are written first in the triangle names. Likewise, angle B and angle E are in the middle of the triangle names, so they are corresponding or congruent. Notice that they both have two little marks in them. The two little marks means those are the same. And you've probably already figured out that since C and F are both last, we would say that angle C and angle F are congruent to one another. I can do the same type of a matching with the sides. Notice that side AB is the first two letters in the triangle name. It's going to match to side DE in the other triangle. Notice that AB is here. It has 1, 2, 3 congruence marks in it. I come down here to DE. It has 1, 2, 3 congruence marks as well. So AB is congruent to DE. Now, if I was being much more formal, I would actually have a little line drawn above AB and DE indicating that these are segment AB or side AB and side DE. But for the sake of keeping this simple, I'm not going to do that today. I look again, I can see that B is the second letter, C is the last letter. BC is this line right here across the top right. Notice there is one mark in it. BC is going to be the same size as EF. EF is down here. Notice that it has one congruence mark in it as well. Can you figure out the last pair of corresponding or matching sides? Hopefully you realize that AC, this one right here with two marks in it, is the first and last letter in the name, meaning it's going to match to DF, which is down here with two congruence marks in it as well. Simply by stating that these two triangles are congruent, I learn 6 different things about the components or pieces of these triangles and how they're related to one another. Now, one thing that does make this problem fairly simple for us is the fact that A, B, C, and D, E, F are both arranged the same way, meaning that I didn't flip it upside down, I didn't spin it around, because sometimes if we do that, it makes it a little harder to match things up. When we do things like that, it's especially important for us to double check with the triangle names to see what is going to match to what. So for example, let's say I gave you that triangle NOT was congruent to triangle KUL. Triangle NOT is congruent to triangle KUL. And I say find the measure of each of the following. And I ask you for the measure of angle T. Angle T. Now, when you look at these, notice they're not arranged as nicely and neatly as the triangles on the previous slide. Instead, I have either spun this around or flipped it. I've done some things to make this look a little bit different than this. It's oriented differently. So when I'm asked about angle T, I'm not going to come over here and just look at the picture and see what angle T is because it's not given to me. Instead, what I'm going to do is I'm going to look up here and say, oh, angle T is going to be the same size as what other angle? Well, it's the last letter in the first triangle, therefore it's going to match the last letter in the second triangle, which means angle T is going to be congruent to angle L. Do you know how big angle L is? Well, hopefully you can look and see that's 109 degrees. Since angle L is 109 degrees, that tells me that angle T is also going to be 109 degrees. And so I'm just going to list that right over here. Get the idea? Once I know bits and pieces about one of the triangles, I can use that knowledge and match it up with pieces of the other triangle. How about this one? The measure of angle U. I would recommend, if you need a second, pause the video, see what you think it matches to, and then restart the video to see what I'm doing. I look down here at U. U does not have an angle measure in it, so I come up here and say U is in the middle. It's going to be the same as angle O. Angle O up here is 28, which means angle U must also be 28, and so I can write that one down. Getting the idea? Here's something interesting for you. Do you know how big angle K is? Again, you may want to pause the video and try that on your own before watching me explain it. I think you can figure that out on your own. Hopefully you've realized that we don't know angle K, but we do know that angle K matches to angle N. Unfortunately, we don't know how big angle N is either. We have to use something else that we learned in a previous lesson in order to figure that out. Do you know what that is? Again, pausing the video if you need time to think. I'm going to go ahead and jump in here and tell you that we know that all 3 angles in a triangle always have to add up to be 180 degrees. So if angle T is 109 and angle O is 28, we should be able to subtract those from the 180 to see what's left for the N. Same thing down here. If angle U is 28 and angle L is 109, we should be able to subtract those from 180, and whatever's left over belongs to angle K. Do you know what that degree measure would be? Well, I subtract that, and I end up with 43 degrees. So I fill that in here for angle K. Well, if angle K is 43, and I know angle K matches to angle N, that tells me that angle N is also 43 degrees. Again, it's just a matter of using what we know as well as the fact that the triangles are congruent to fill in missing pieces of information. I want to do the same thing with the sides. Can you figure out how long side ON has to be? Once again, pausing the video if you need a second to think. I'm going to look up here and see ON is going to match up to UK. UK down here is 17 inches. So ON must be 17 inches as well. How about KL? Can you do that one? Again, pausing the video if you need to. K is first, L is last. N is first, T is last. So NT and KL should be the same size. I happen to know that NT is 5, which means KL must be 5 as well. One more. UL. UL matches to OT. OT is 9, therefore UL is 9 as well. I think these are fun. To me, this is kind of like a little puzzle where I'm just working back and forth, taking what I know and using it to find out other pieces of information. Here's another problem, very, very similar to this. This is triangle BIG is congruent to triangle DEL. We want to see if we can find some missing pieces of information. Again, I'm not going to ask you to pause between each problem, but I am going to suggest ahead of time you do that. And then as you need to, just pause and restart. This is the only time I'm going to mention it on this slide. Angle D matches to angle B. Angle B is 35, so angle D must be 35 as well. How about angle I? Angle I matches to angle E. Angle E is 45, therefore angle I is also 45. Not too bad. Do you remember how we find angle G? Ordinarily, I would take angle G and match it to angle L. Unfortunately, I don't know angle L either. What I do know is that every triangle has to add up to 180 degrees. So 180, take away the 35 we used here, take away the 45 we used here, and that leaves us with 100 degrees. Once you know angle G, of course, angle L is the same. It is also going to be 100 degrees. How about side DL? Side DL. Notice it's not shown here, but we do know it's first and last, which means it's going to be the same size as BG, which means it's a 10. GI, again, it's not shown, but GI is going to be the same as LE. LE is 8, which means GI must be 8. And one last side, DE. DE is the first two, which means it's going to match to BI. It's 22, which means DE is 22 as well. Hopefully that doesn't seem too bad for you. I do want to point out a couple things. First of all, you'll notice that if you look really closely at this, this probably is not actually 100 degrees. It actually looks closer to being a 90-degree angle. Also notice that if this is 8 centimeters, this is probably not 22. In fact, what I do is I take triangles, I insert them in here, and then I just put in numbers that, that look fairly close to accurate. I don't actually calculate those out. It's important for you to realize that because sometimes students will get in the habit of just looking at a shape and saying, oh, well, it looks like it's this many centimeters, or it looks like it's this many degrees. You need to make sure that you can't, or that you don't try and use that as a justification. In geometry, it's very important that you can support whatever decision you make. For example, if this is labeled 8, then I know this has to be 8 because of the definition of congruent. That is a geometric proof or substantiation of the thought. Don't just get in a habit of saying it just looks like it, especially if you're using a teacher's worksheet or something like that, because generally I'll take the same pictures over and over again. I'll just change the numbers around. It's a lot easier than trying to make sure that every single number matches to the exact 1/10 of a degree or whatnot. Hopefully that makes sense for you. Hopefully you've got the idea of congruent figures. Remember, you should be able to look at this name and you should be able to match all the matching corresponding angles. You should be able to match all the corresponding sides as well. Likewise, in these last two slides, if I give you specific pieces of information, there's a lot of other pieces of information you should be able to find as well. But all of that is contingent on whether or not the shapes are congruent. If the shapes are not congruent, we cannot match things in the exact same way. Now, here's the good news. In order for us to know if triangles are congruent, we don't actually have to check every single side and every single angle. So I want to talk for a few minutes about the congruence theorems for triangles. A theorem is just a fancy name that just means a rule that we have proven or something that we know is true. Like, for example, this one here. If I know all 3 sides of a triangle, there's only one triangle that I can make. I'm going to do my best to try and illustrate these for you using some pictures. Ordinarily in my class, we would play with something known as an angle leg, where we can look at different possible combinations of sides and angles of triangles and try and develop this theorem. That's not entirely possible here in a video, so we're just going to do the best we can. If you need to pause and think about what we're saying or rewind or rewatch a portion of this, I would suggest you do that as well, but hopefully as I walk through these different theorems, you're going to see that they should make some sense. So let's try this. I've got three sides of a triangle, a blue, a red, and a purple side. If I were to take my blue side and my red side and my purple side and put them together, this is the only triangle they can possibly make. Now, I could have put the red up here across the top and put the purple down here, or I could put the blue across the top and the purple. And there's different ways that I could turn or rotate or flip this triangle. But here's the key for us to remember. If we know how long this side is, we know that the purple side has to connect to the blue and the red has to connect to the blue, and they have to be a length where they're going to touch each other. Because these are the only three lengths, this is the only triangle that's possible. If I were to try and make this angle larger, then what would happen is my blue would come out this way and my purple would reach the other end. Likewise, if I were to take this blue and try and make it an angle smaller, the purple's going to be too long. These sides are going to force these angles to be a certain size in order for them to meet at their endpoint. Otherwise, it's not going to construct a triangle at all. So if you have two triangles and you know that all three sides are congruent, then we know the angles are also going to be congruent. The sides force these angles to be a particular size. So if you know how long all three sides are, you don't need to know the angle measures in order to tell that the triangles are congruent. This is called the side-side-side theorem for triangle congruence, or sometimes we abbreviate that as the SSS theorem. If we know all three sides of two triangles, if we know the sides are going to be the same, then we know that the triangles are going to be congruent. Here's a second theorem. If I know two sides of a triangle and I know the angle that connects them, then there's really only one triangle I can make. So let's say I have a blue, a green, and I'm going to make this red angle right here. If those two sides are connected at a 43-degree angle, and I want to build a triangle, that triangle has to have a third side that is the length between these two dots right here. If it's shorter than that, it's not going to reach the other end. If it's longer than that, it's going to stretch beyond the end and it won't be a triangle anymore. The fact that this angle is fixed or cannot change means that there's only one distance or one specific side length that will make this into a triangle. And in fact, I can illustrate that by putting a purple side in here. If this purple side is any longer, it's not going to be a triangle anymore. If it's shorter, it's not going to be a triangle anymore. I can't change the angle because the angle is fixed. Therefore, if I have two triangles and I know how long one side is, and I know how long the second side is, and I know how big the angle that connects them is, the third side is going to be forced to be a specific length. And that's going to force these other two angles to be a certain angle, which means the two triangles must be congruent. That's called the side-angle-side theorem, or sometimes we abbreviate that as SAS. I have one more for you. If I know two angles of a triangle and the side that connects them, then there is only one triangle that I can make. So I'm going to take maybe a 30-degree angle and a 60-degree angle, and let's put the blue side in here. Notice this blue side is different from the other blue sides. I've got two angles and a side. I take the first angle, I draw the line, and I have a second angle. Notice it's an angle, the side that connects the angles, and the second angle. If I know those three pieces of the triangle, when I extend those sides so they cross, when I extend this missing side and this missing side so they cross, notice they're going to cross at a specific point. So I don't really need to know how big this and this side are. If I know that both triangles have a 30-degree angle and a 60-degree angle, and I know how long this side is, then the second and third side are forced to be a specific length. That also forces this third angle to be a specific angle. If two triangles have angles and the included side congruent, then the triangles are congruent. We call that the angle-side-angle theorem, the angle-side-angle theorem, or sometimes we refer to it as the ASA theorem. Now, these three theorems are the only three congruence theorems that we have for triangles. And I make sure I make a point of that because there are two other patterns that people think are theorems for congruent triangles and are not. I want to talk about those two real quick. People often ask me about the angle-angle-angle theorem. In other words, if I know all three angles of a triangle, maybe I've got a 30, a 60, and a 90. People say, well, if two triangles have all the angles the same, does that make them congruent? Well, let's see. Here's a 30, here's a 90, and here's a 60. You can see that that forms a triangle. But I can take those same 30, 60, and 90-degree angles, and I can actually build a larger triangle. This is not a congruence theorem because these two triangles are not the same size. Notice their angles have the same measures, but their sides do not. The sides are actually proportional. Do you remember the name for shapes that have all angles congruent and all sides proportional? Those are similar. These two triangles, if I know all the angles, they will definitely be similar triangles, but I don't have enough information to determine if they are congruent or not. I need at least one side to make that determination. The angle-angle-angle theorem proves similarity. It does not prove congruence. And then there's one more. It's the angle-side-side theorem. If I know two sides of a triangle and an angle that is not the one that connects them, what can we determine? Well, let's say I've got a 30-degree angle and I have two sides. So I'm going to draw that angle. I'm going to draw the first side, and then I'm going to take this second side, and I'm not going to draw it here. I'm not going to draw it so that we have side, angle, side. I'm going to connect it up here at the top so that I have an angle and then two sides in a row. Here's the problem. I could connect it like this, which means this last side would be really small, or I could do the exact same thing over here, and I could draw that second side out into an obtuse angle. Notice that this tiny little triangle and this large triangle are not the same. Even though they both have a 30-degree angle, even though they both have a blue side that's the same length and a green side that's the same length, without knowing this angle right here, my third side could either be really long or it could be really short. The two triangles might be congruent, or they might not be congruent. If this is all the information I have, I can't tell which of the two triangles I'm looking at. I can't be sure. This theorem proves nothing. So I'm really incorrect to call it a theorem. I should call this a not theorem. Now, a lot of my students get some kicks and giggles out of the name, but I like to use this name as an illustration to remind you that this is not an appropriate theorem. This is not one that you should be able to use in a math class. So now that we know three theorems for determining congruence, we know one theorem for determining similarity, and we know one non-theorem, what we ought to be able to do is we ought to be able to take a look at two triangles, and we should be able to tell whether they are congruent or not. Remember, if they are congruent, or in order for you to tell they are congruent, they either need to have all three sides the same, a side, a second side, and the angle between them the same, or two angles and the side between them the same. That proves congruence. If all you know is that all three angles are the same, then they will not necessarily be congruent, but they will be similar. And if you know an angle and two sides, but the angle is not between them, then you have this non-theorem. It proves nothing. Looking over at this picture, notice that I have a 13, an 80, and a 15. I have a 13, an 80, and a 15. That is a side, an angle, and a side, or two sides and the included angle. That tells me that these are congruent. Notice I answered the question, yes, triangle EAT is congruent to triangle COW using side, angle, side. Now, ordinarily, I don't like using abbreviations. I like my students to be very specific. This is one of the few exceptions because it is common among lots of mathematicians to abbreviate this way. So if your teacher says it's okay, I have no problem with you abbreviating like this. Get the idea? I'm going to put another setup here. I'm going to recommend you pause the video, make the determination on your own, then restart the video to see if your decision matches mine. Notice I have a 60, an 11, and a 50. I have a 60, I have an 11, and I have a 50. It is an angle connected to a side, connected to an angle. This is congruent using angle, side, angle. Notice I answered the question, I said they are congruent, and then I explained how I knew. Make sure you include all three parts. You should be getting pretty good at this point. Let's try another one. Are they congruent? Again, pausing the video if you need some time to think about it. I'm going to go ahead and tell you that no, they are not congruent. Triangle MTN is not congruent to triangle DEW, and we know that using side, side, side. Notice that the 8s are the same size, the 19s are the same size, but 10 and 11 are not the same size. They are not the same size. That tells me that angle E is larger than angle T. Those are not congruent. Not that that's what we're talking about today. By the way, there is a symbol for not congruent. It has a congruent sign with a slash through it, but for now I'm just using the word not. How about this? What do you know about these? Again, you've paused the video, you've tried this on your own. These are similar. These two triangles are similar to one another. I can't tell if they're congruent because all I know are the three angles. So these might be congruent, or one might be larger or smaller than the other. They are definitely similar. Notice that I did go through and remind you of the similar symbol. How about these? Can you tell anything about these? I'm assuming you've already done that with the video pause. You can't tell anything about this because what you're given is an angle side, side, and the angle is not between the two sides. If you knew angle D and angle M, you might be able to prove something, but the way it is, you cannot. How about this one? Hopefully, you realize that these are congruent using angle, side, angle. Notice that triangle DIG, I have side DI. And triangle DUG also has side DI. And I did put a little congruence mark in there. Since they share that side, we know that side is going to be congruent in both triangles. They're both going to be the same. That's actually a geometry rule, is that a side is always equal to itself. And it comes up a lot when we are sharing them. But I have the 20 in both, and then I have the side, and then I have the angle. This is angle, side, angle. How about this one? Once again, notice that we have this shared side right here. I have side IC is congruent to side OC. I have side IT is congruent to side OT. And of course, CT is congruent to itself. This is congruent using side, side, side. How about that one? Hopefully you were able to figure out that no, these are not congruent because we have an angle, side, angle, but that second angle, they are not congruent. Angle G is not congruent to angle N. So we can prove these are not congruent using angle, side, angle. That's basically it. Hopefully that has made sense for you. If not, take a second, watch it again. I think it should. The important thing is to keep straight which rules prove what. Don't forget you can use the abbreviations. Just be extremely careful with the fact that angle, angle, angle does similar or proves similar, not congruent, and that this is a non-theorem. This is not a rule. If you do that, you should be in good shape. As always, I do wish you the very, very best. You guys take care of yourselves, all right? Bye-bye.